Welcome to our session on RCCL, NCCL, and the NVIDIA Collective Communications Library. Presented by Patrick Lemoine, we will explore advancements in these technologies as of 2026. We'll explore the technical architecture and advancements in multi-GPU communication for high-performance computing and artificial intelligence training. Collective communication is crucial for modern artificial intelligence training and high-performance computing, which use thousands of graphics processing units per job. It supports model, data, and pipeline parallelism through operations like all-reduce and broadcast. NCCL and RCCL abstract complexities, allowing developers to concentrate on model development rather than hardware specifics. NCCL, or NVIDIA Collective Communication Library, is a standalone library designed for efficient multi-GPU and multi-node communication. It's optimized for NVIDIA GPUs using technologies like PCIe and NVLink. Unlike MPI, NCCL focuses on GPU to GPU communication, primarily for distributed training in frameworks like PyTorch and TensorFlow, and supports C, C++, CUDA, and various front ends. NCCL offers key features like collective primitives, such as all-reduce, broadcast, and reduce. It supports topology-aware routing over peripheral component interconnect express, NVLink, and more, often requiring zero configuration. Its single-kernel design fuses communication and computation for low-latency, high-bandwidth performance. Additionally, it supports multi-communicators and integrates with Compute Unified Device Architecture streams for asynchronous operations. RCCL, AMD's ROCm Communication Collectives Library, mirrors NCCL for ROCm-based GPUs like Instinct and Radeon. It supports standard collectives such as all-reduce and broadcast. RCCL is topology-aware, utilizing PCIe and GPU interconnects. It functions as a standalone library or integrates with PyTorch and TensorFlow, offering compatibility with NCCL 2.2.2.3 and newer. ROCm is AMD's open-source high-performance computing artificial intelligence stack, including HIP, ROCm Machine Learning, and ROCm Collective Communications Library. ROCm Collective Communications Library serves as a backend for PyTorch distributed data parallel, Horovod, and custom distributed training loops, mirroring NVIDIA Collective Communications Library's roles. It offers a similar application programming interface for portability, with tools like RCCL tests and the open-source ROCm RCCL on GitHub enhancing tuning and debugging. Let's explore communication primitives in NCCL and RCCL. All-reduce allows each GPU to send a buffer and receive a reduced result. All-gather concatenates chunks from each GPU. Reduce sends the result to a root GPU, while broadcast shares data from one GPU to all. Reduce scatter partitions the global reduction result, and point-to-point handles direct sends and receives. In NCCL, a NCCL COM or communicator is created for each GPU group. Each GPU is assigned a rank, serving as its logical identifier within the communicator. Channels map to PCIe, NVLink, NIC links, enabling parallel bandwidth. Grouping with NCCL Group Start and NCCL Group End allows for efficient collective operations. Topology detection involves identifying physical components like PCIe switches and NVLink. Logical topologies are constructed over these using NCCL, RCCL. Dynamic detection at startup optimizes communication by probing GPUs and interconnects. Channels are mapped across different links to maximize bandwidth and prevent hotspots. Ring-based collective algorithms, like ring all-reduce, form a logical ring where each graphics processing unit communicates with its neighbors. The scatter-reduce-all-gather variant splits data into chunks for partial reduction. This approach offers high bandwidth utilization, with latency increasing linearly with more graphics processing units, making it ideal for large messages and numerous graphics processing units. Tree-based collective algorithms utilize a binary tree structure, where each graphics processing unit has a parent and up to 2 children. The double binary tree enhances bandwidth by ensuring each node is non-leaf in only one tree. This approach offers logarithmic latency growth, making it ideal for small to medium messages and low latency scenarios. The PAT algorithm enables each GPU to communicate directly with every other GPU, ideal for workloads with dominant all-to-all communication. It offers high bandwidth potential, but requires complex topology management. Often used in specialized scenarios, it can be combined with ring or tree topologies for hybrid strategies. NCCL offers a variety of algorithm variants like ring, tree, and pat. It selects the optimal algorithm for each collective and message size using a tuning model, which can be calibrated with NCCL tests. Users can override this with environment variables, aiming for optimal performance on NVIDIA platforms without manual configuration. NCCL primitives are stream asynchronous, allowing NCCL all reduce to launch on a CUDA stream. This non-blocking approach enables computation and communication overlap on the same graphics processing unit, eliminating the need for host-side buffers. For distributed data parallel and high-performance computing applications, this results in significant performance gains by pipelining forward, collectives, and backward, stochastic gradient descent steps. NCCL APIs in C++ and CUDA offer robust communication primitives. The C API, accessible from C++ and Python, includes functions like NCCL commit_all and NCCL all reduce. In single-process multi-GPU setups, use NCCL commit_all followed by NCCL group start and multiple NCCL all reduce calls. For multi-process setups, NCCL getUniqueID is used with message passing interface for initialization. PyTorch Distributed Data Parallel (DDP) leverages NVIDIA Collective Communications Library for efficient GPU communication. By default, the backend is set to NCCL, which can be specified using init process group backend NCCL. DDP wraps models in distributed data parallel, synchronizing gradients with NCCL all reduce. This setup offers automatic topology handling, native multi-node scaling, and fine-grained control through NCCL RCCL environment variables. In ROCm PyTorch, distributed data parallel can utilize RCCL on AMD GPUs, maintaining the same API as NCCL. The logical workflow mirrors NCCL-based DDP, with performance influenced by PCIe, InfiniBand topology, and ROCm optimizations. This is ideal for high-performance computing centers using ROCm stacks and cloud instances with AMD Instinct GPUs. The NCCL 2.x family, versions 2.23 to 2.26, enhances tuning models and supports larger clusters. It introduces profiling and debugging features, cross-node and multi-NIC network interface card support, and integrates with CUDA, Compute Unified Device Architecture, graphs for static execution. Robustness improvements include deadlock detection, enhanced error messages, and launch ordering fixes. NCCL 2026 introduces cross-data center communication, enabling topology-aware routing across multiple centers. It enhances algorithm extensibility, allowing easier integration of new algorithms and transport plugins. Profiling and tooling improvements include enhanced CUDA kernel profiling and debug log timestamps. Quality of service per communicator offers traffic shaping for multi-tenant clusters. Implicit launch order helps prevent deadlocks when sharing graphics processing units. Training jobs across multiple data centers face challenges in capacity and geography. NCCL addresses this by constructing intra-data center trees and chaining data center routes into a global tree, optimizing bandwidth and scalability. The typical pattern involves intra-data center reduce scatter, inter-data center all reduce, and intra-data center all gather, ensuring efficient topology-aware communication. RCCL 2025 introduces compatibility with NCCL 2.22.3 and newer, supporting MI300 series with all 8 graphics processing units per node. It includes RCCL disable rail trees for reverting tree building methods. LL128 models offer range-based tuning per graphics processing unit architecture and network interface card. By 2026, expect improved cross-node and multi-network interface card handling, aligning closely with NCCL tooling and profiling. NCCL Tests is a benchmark suite measuring bandwidth and latency for operations like all reduce and broadcast. It's crucial for calibrating NCCL RCCL tuning models. Key profiling tools include NCCL debug and CUDA profiling. Best practices involve running NCCL tests in your cluster and tuning with NCCL max in channels and NCCL min in threads as needed. Explore NCCL error codes like NCCL success and NCCL unhandled CUDA error. Use debug modes such as NCCL debug info and NCCL debug dumpy1 to diagnose issues. Common problems include misconfigured topology and deadlocks from multi-communicator misuse. Ensure consistent environments to avoid errors. The 2026 NCCL roadmap focuses on enhancing multi-network and multi-NIC robustness, improving transport plugins, and refining communicator and channel management. Developers will benefit from advanced debugging tools and clearer channel launch order insights, reducing hang issues. These improvements aim to optimize performance in large-scale, multi-tenant cloud or high-performance computing environments. RCCL 2025-2026 highlights include full compatibility with the NCCL API and NCCL 2.22 style tuning, support for modern AMD Instinct node topologies like the MI300, and mature benchmarking with NCCL tests. Looking ahead to 2026-2027, expect tighter integration with the ROCm HPC stack and performance parity with NCCL on comparable hardware. Use NCCL for training on NVIDIA GPUs and integrating with frameworks like PyTorch and TensorFlow. Opt for RCCL on AMD Instinct clusters for NCCL-compatible API and tooling. Choose based on GPU vendor. NVIDIA means NCCL, AMD means RCCL. Ensure code hygiene by using NCCL comminit rank and NCCL comminit all cleanly, and always destroy communicators and streams. For launch order and deadlocks, use NCCL launch order implicit 1 in debug mode. Profile and tune by running NCCL tests on your cluster, and set NCCL debug info in continuous integration using trace for deep debugging. NCCL and RCCL are essential for managing collective communication in larger clusters with more GPUs. They will support cross-data center trees and multi-network setups, becoming standard with quality of service per communicator. Integration with frameworks like PyTorch Distributed Data Parallel, DeepSpeed, and Megatron will deepen, minimizing direct application programming interface interaction for developers. NCCL and RCCL are essential for GPU-optimized communication, offering core primitives and topology-aware routing. By 2025-2026, expect advancements in cross-data center capabilities and robust multi-NIC support. Developers should master primitives, understand algorithm choices, and utilize tools like NCCL tests for efficient implementation. Thank you for your attention.